Okay, so this video refers to Lecture 7, and specifically the internal forces part of Lecture 7. So we thought about all the loads and things on the externals, the frame, or the machine that we're analysing. We're now going to think about the internal forces acting in members. So if you look at the PowerPoint that goes with Lecture 7 on internal forces, you'll see a couple of applications on slide 4 and 5 and 6. You've just got different structures, and we've done in previous lectures how you'd analyse the forces acting at different points and the moments acting at different points. What we're now going to do is analyse what's actually happening inside of the members, and obviously that's useful for when you're designing these things, so you can choose the right material to work in these members. So if we jump a couple of slides and we look at slide 7, I'll quickly sketch slide 7. So this is just an example of what you consider when looking at the internal forces. So that's a typical scenario, and we can consider cutting the beam at point B, and then drawing free body diagrams for each half of it individually, or for one half of it, if we only are interested in one side, and forming equations of equilibrium for that side. So if you imagine that's it's a little bit like, if we ignore the forces at the ends for now, so the forces at the ends, you can have a support reaction to each end, and you could have a Y, let's say an X reaction at this point here. This is point D. You could have an X reaction because that's a pin joint, but you can't at point A because it's a rolling joint. But if we just focus on what's happening at B, we're pushing on the top of B. Well, that's kind of like if you imagine B is going to break there. Imagine that's like two fingers of a Kit Kat from the end, and you're pushing down there trying to snap them in half. So you're going to end up with two parts, two separate fingers. Admittedly, you get a little bit down there. We're going to ignore that for now. That's just for any pedants that are listening. So there's three different sorts of force that are going to exist on both halves during the time you're trying to break it. There's going to be a turning effect. So if you imagine when you break your Kit Kat eventually, you end up doing that as it breaks, and it comes apart, doesn't it? The fingers bend towards each other, and they're designed to do that. Well, that's still happening in this scenario. So there's a turning effect on that side, and there's a turning effect on this side, and they're equal and opposite. So MB, MB. Equally, there is a normal or an axial effect. They're pushing against each other. Equal and opposite, NB. But finally, there's a shearing effect. Each side is trying to push past the other side. So, again, equal and opposite. And shear force is the one you may not have used before, VB. So we've got the turning effect, MB, the moment. We've got the axial or normal force, NB, where they're pushing against each other, and shear force, VB, where they're trying to push past each other. Now, if we consider what's actually happening there, all of those effects on each side are equal in magnitude and opposite in direction. So when we put it back together, if we imagine it's one beam again, then there's no net result overall. So there's internal forces at work, but they're going to cancel out to give no net result. So what we'd do if we were trying to solve a problem is we'd take a cut along the place where we think it's going to be easy to analyse, draw free body diagrams for each side, label up the forces that are acting, and then see what equations of equilibrium we can apply. We'll do that now. We'll look at the example beginning on slide 10. I'll draw it and then I'll show you how to solve it. So that's our scenario. That was for slide 10. So the first thing we do is draw a free body diagram of that. So we've got our bar, we've got this first area on the left hand side, 3 kilonewton per metre distributed load, acting 6 metres across. Well, I can replace that with one force acting 3 metres in. 3 times 6 is 18, so it's going to have a magnitude of 18 kilonewtons, because we did 6 metres times 3 kilonewtons per metre. We've also got a rolling joint at point A, that's meant to be an A just here, and A is 6 metres in, so another 3 in from the 18. We're going to have another force, a support force in the Y direction, AY, and finally another 9 metres, so 2 times 4.5 in. At B, we're going to have a BY, and we're going to have a BX, because that is a pin joint. And we want to know the forces acting. So, first thing we can do is we can start to do equations of equilibrium with what we've got. So we can say the sum of the forces in the X equals Bx equals 0. And you can see that because there's no other forces acting in the X direction. We can also take moments about point A to find By. So the sum of our moments about point A is equal to minus By times 9. And that's because it's going to be turning it clockwise, so it's minus and it's 9 metres away from A, plus 18 times 3, and that 18 is going to try and turn it anti-clockwise about A, and that all equals 0. So we can say By equals 6 kilonewtons. Now, we're only asked for certain things. We're actually asked for the internal forces at point C. So now we've got some of the new information we need. We've got all the forces for one particular side of point C. We can now redraw the free body diagram just considering the right hand side. So if I do that, this is now point C, this is point B, and we know that there's 6 kilonewtons acting down here because we've just calculated it. We know that the length of the piece is 4.5 metres, and we're going to assume a moment at C that way, a shear force at C that way, and a normal force acting that way. And again, if these come out negative, we can just, as we've done before, say, okay, it's acting in the opposite direction. Well, now we can start to apply our equations of equilibrium. You should spot very quickly that the sum of the forces in the X is going to be NC, which is going to be 0. The sum of the forces in the Y direction is going to be 6 kilonewtons, and that's minus because it's going downwards, and a minus VC, so equals 0, so VC equals minus 6 kilonewtons. In other words, our shear force is acting the opposite way to the way we believed. And finally, our sum of our moments about C is equal to minus 6 times 4.5 minus MC. So MC equals minus 27 kilonewton meters, and that's come out minus, so that's also acting the opposite way to the way that we believed. So that was a very simple problem looking at the internal forces. Really all we've done is introduce the 3 different sorts of force and moment that you'd apply to a point where you'd break the beam, and then ask you to solve them. There is a group problem solving exercise on slide 14 that begins, so if you pause the video and have a go and then come back when you're ready to see the solution. So you should now have had a go at the group problem solving exercise beginning on slide 14 of lecture 7 on internal forces. So what we'll now do is we'll look at solving it together. So point A was a pin joint, and the beam was 6 metres long. So we'll draw a beam of 6 metres long. point A, we've got a point B on the other end, we've got a point D that I believe is in the middle. And then in terms of forces, we've got a tension force here, we've got a tension force here in the middle, and that's 45 degrees. That's going to be the same tension because it's the same rope going up to C. And then we've got AX and AY, and we've got a force downwards here, and with the distributed load, it's saying 300 newtons per metre, and it's 6 metres long, so we're going to have 1800 newtons acting downwards. And then what we need to do is start filling in some of these blanks. So the first thing that it'd be good to do is find the tension. So some of our moments about point A will mean we can ignore all of these unknown A's, and we can say, okay, the tension times 6, which is the tension at B, so it will be this tension first of all times 6, positive because it's going anti-clockwise, plus T sine 45. Now if you're following this in the lecture PowerPoint, there is a typo here, that should be times 3, and that will give you this component of T at point D, so that's times 3 because it's 3 metres away it's acting, minus 1800 times 3 equals 0. So our T equals 665 newtons. That's our tension. Now we've found that, we can break off into 1/2 of the beam. We're actually asked for the internal forces at point F, which I haven't marked on my free body diagram, but it's halfway between D and B, so it's kind of there. That would be our point F. Now it's going to be much easier to work on section FB because we've got all the forces that are acting there. So I'll just jump to the next slide and we'll redraw that. So FB, we've got a tension we worked out as 665 newtons. We've got a shear force VF. We've got a moment MF. We've got a normal force NF. We've also got a distributed load acting. Now, we worked it out for the whole beam earlier, so for the whole beam earlier it was 1800 newtons acting bang in the middle. For this short section is only 1.5 metres long, and it's 300 newtons per metre along the whole of this section. So we can say there is 450 newtons acting downwards exactly halfway, because it was 300 newtons per metre. This section is 1.5 metres, so that's 450 newtons, and it's acting halfway along this section of beam. And then we can start to do some of our forces and equations of equilibrium again. So the sum of the force in the X is going to be NF. There are no other forces in the X, so that equals 0. Our sum of our forces in the Y, we're going to have minus 450, which is our distributed load in the middle there, plus 665, which is our tension, minus our shear force. It's going to be 0. So our shear force is going to be 215 newtons. And finally, we're going to have some of our moments at point C. Hold on. And here's that point C in the lecture notes is also incorrect. That should be point F. That equals 665 times 1.5, and that's going anti-clockwise, so it's positive, minus 450 times a 0.75, and it's a minus because it's trying to go clockwise, minus MF equals 0. So we can say MF equals, am I going to run out of room? I don't think so, 660 Newton meters. That should be an NM. So that was 2 sample questions on how you would solve questions about internal forces in members, and concludes the first video for Lecture 7 looking at solving for internal forces. There are a couple of other videos in this lecture regarding stress-strain, Poisson's ratio, and some other little bits that are all grouped together. So there are 2 other videos in this series to look at as well.